Hello and welcome back once more to another lecture on the NPTEL course on the advanced plasticity of solid continua. We have been discussing about the representation towards the fag end of the last lecture. We were talking about the representation of the dissipation potential, a principled way of representing it. Now it turns out that the notion of the support function does that job. Let us quickly see what it is, right. So let us consider C to be closed and convex, right. C is the space or the set of all admissible stresses. Now the support function over this set C, but note that the support function is not a function of the stress, it is a function of the J, that is the thermodynamic fluxes like the strain rates and things like that. The support function over C of J is the supremum over the set C for all x which are thermodynamic forces of this inner product of x inner product with J. So since you are taking supremum over x, the x dependence goes off, so you are left with a function of J only, right. So this inner product here is an appropriate Euclidean inner product, okay. We are not talking about a more complicated differential geometry than the Euclidean sets here. So now let us quickly take a look at this nature of this function. This turns out to be a convex function. It is also positively one homogeneous. You can easily see that this is a good exercise for you to try and check based on the basic definitions of convexity and one homogeneity, that indeed HCJ is a convex set and one homogeneous. And then if I can find HCJ given the set C, then my phi j, which is basically the dissipation potential, is nothing but that HCJ, right. So it is a pretty simple way and a very principled way of finding out for rate independent plasticity the dissipation potential, right. So this is basically by definition the supremum over all sigma 0, the deviatoric stresses of the inner product of sigma 0 with the fluxes J. Geometrically what does it mean? Let us take a look, okay. So it is here, HCJ is the signed distance from the origin of the stress space, the set C, that is 0 stress basically, to the supporting hyperplane of C, supporting hyperplane, you remember. So if this is the set C, right, this is the set C, this is my origin of the set C. So suppose the J is acting this way, okay, this is my action for J. Then you have to go to this supporting hyperplane such that the sigma, in order to ensure that this product is the maximum, sigma 0 must act in such a way that this sigma 0 is normal to this supporting hyperplane here. So basically you draw a line from the same point to the closest point on which this is normal, okay, right. If you draw it along J, it is not normal, but if it is a circle, pure sphere, then you see if J is acting this way, sigma 0 is also acting this way, you understand. So for a non-sphere they are not co-directional, but that is the anisotropic case, but for purely von Mises like thing they are co-directional, right. So this is what this is the signed distance from the original to the supporting hyperplane. This is one supporting hyperplane. Then like that you can go on constructing a lot of such supporting hyperplanes, and if you do that you will see finally you will be generating this curve only, that del C, right. So that is why there is a geometric meaning to this supporting hyperplane. So in this sense the dissipation potential is something like, if you plot all these supporting hyperplanes, right, then essentially what you are doing is you are generating the outer envelope of the yield surface, right. So basically that is what the dissipation potential is, something like the outer envelope of the yield surface. Okay, so here basically we are doing exactly the same thing. We are trying to understand it from the same perspective that I drew from a schematic. The important point here is that by actually choosing the Hc equal to phi j with the supremum included in the definition of Hc, we are automatically maximizing the plastic power, you see, and therefore this is also correspondent to the maximum dissipation, consistent with the maximum dissipation principle. On the other hand, what happens if basically if there is a something like this, think about it, you know, like Tresca plasticity, if the supporting, you know, if the yield surface turns out to be hexagonal, then actually what will happen? You will see that, you know, if J is acting, let us say this way, right, then, you know, this sigma 0 also have to be acting this way, acting along this, because both are perpendicular to this face, right, or this face, any face, right. On the other hand, if you are at a corner, right, then the supporting hyperplane, that notion is not clear. This can be a supporting hyperplane, right, this can be a supporting hyperplane, this can be a supporting hyperplane, this is also a supporting hyperplane, this is also. So that is how you get the normal cone, right. You get all sorts of possible values which are within this set. This is perpendicular to this is perpendicular to this. So in this, you know, the plastic strain rate can live, right. So anyway, so this is what the normal cone is. This is basically the normal cone. I told you, I will explain to you at some time the notion of the normal cone when it is non-trivial. This is one such case of Tresca plasticity at a corner, where the normal cone will consist of several possible different plastic strain rates, not one. Anyway, so let us talk of the usefulness of this entire approach, right. So in isotropic plasticity, the support function of a sphere, is just the norm of J, okay, the radius of the sphere. In the anisotropic case, that is more interesting, the Hill's anisotropic for example, in which sigma y could be dependent on the direction in which the flow is occurring, right, not the same in all directions, right. That is where the interesting thing comes up, further interest, because C in that case could be an ellipsoid, right, something like this, sorry, so this is something like this, correct. So you see, so in such a case, the fact that sigma 0 belongs to del phi of J, right, does not mean that J and sigma 0 are collinear, because that will not maximize the plastic power. If J is in such a, suppose this is some center, okay, J is acting like this. Now if I take sigma 0 to be collinear, then that may not be the maximum plastic power, maybe somewhere here, because this is a much bigger sigma 0, correct. So even though there is a cos theta intervening, because you are taking a dot product, right, inner product, but even despite, and cos theta is less than 1 in that case, but despite that, because this sigma 0 is much bigger than this sigma 0, so therefore the total plastic power for this sigma 0 can be much higher, right. So this is a typical case of importance for us. So in the anisotropic case, please remember therefore that the direction of the plastic flow as given by the plastic strain rate and the deviatoric stress are not collinear, okay, they are in two different directions in general. So corners, if there are corners, then of course it becomes even more interesting. It says that in such a case, think of the Tresca plasticity, right. At a corner the normal is not unique, right. So, this is my corner, this is the corner, right. So, this is one face, this is another face meeting at the corner, right. So, you get a normal cone from here, you just put a line which is perpendicular to this face, another line which is a perpendicular to this face, and you get the normal cone here, right. This is basically my normal cone. So, in such a case what happens is that by the same logic that J is an element of del phi star of, let us say, x or sigma 0, x is basically sigma 0, I can say that J can take a value because del phi star sigma 0 is the normal cone at this corner, right. So, J can take any value which lies within that normal cone. In other words, it may turn out that not only are the J, that is the plastic strain rate, and the stress not collinear, but also there could be multiple plastic strain rates possible, multiple directions for plastic strain rate possible for the same sigma 0. That is a very important point, right. So, it is not covered properly in classical plasticity. In all these cases, the support function defines the phi j. Okay. So, the flow rule, what is the flow rule? This is a flow rule. Even if I say that sigma 0 is in del phi of j, that is also a flow rule. So, you can write the flow rule in both the ways, right. It is basically a relationship between the strain rate and the hardening variables and the stresses driving the plasticity, that is the thermodynamic forces x, right. In both the cases it is captured, So, basically the flow rule based on the subdifferential tells us that the possible directions of J lives in a set, the normal cone. That is a very interesting point, right. The one homogeneity of the support function automatically implies, so therefore automatically implies the one homogeneity and hence rate independence of the dissipation potential. Okay. So, when it is rate independent, that is the dissipation potential is one homogeneous, the dissipation depends only on the path, not the speed along that path. Okay. So, remember this, very important. When we say maximum dissipation, we are just saying that the material spends as much energy as is allowed by the support function. So, the support function is the bridge that turns a static object, a static constraint, which is the yield surface, that is, stresses cannot leave C, into a kinematic cost, a dynamic kind of a cost. What is that cost? That is the flow. If you have to maintain the flow, plastic flow, then you must spend phi amount of energy, not below that, right. So, it converts one to the other. They are all the two sides of the same coin. Okay. This makes it very clear. Let us take the simplest case, which is the small strain plasticity of the von Mises type. So, only deviatoric stresses, because this is nearly incompressible. So, let us consider the set of all such deviatoric stresses script S03, which is all sigma, the stress belonging to 3 by 3 matrices of the symmetric type, such that the trace of the matrix is 0. Now, the set of all admissible stresses C will be all sigma 0 of this type, that is belonging to S03, such that the modulus or the norm of sigma 0 is less than or equal to sigma y, the yield stress, right. That is basically the von Mises plasticity. In this particular case, it is a sphere. So, C is a closed ball centered at the origin in the stress space, right. So, what is the support function? We have already discussed this in one context, that for a sphere the support function is such that the sigma 0 and j must be collinear, right, in the same direction. That's what maximizes this, the supremum you get only corresponding to that case, right. So the collinearity of the stress and strain, which is also called co-directionality, is automatic here, right. So in this particular case, what is the maximum value of sigma 0, which is sigma y, correct. So what is phi j? So phi j automatically therefore will be equal to this, right, and this is nothing but, so sigma y here, right. So that corresponds to j acting in the same direction. So basically this phi j will be simply equal to sigma y norm of j, correct. So this is the, this is the definition for our dissipation potential from the notion of the support function, and we can apply the classical optimization problem to this phi j, okay. So if you really want to do that, right, so it is exactly the same case as we have actually solved some time back. We saw fx equal to modulus of x, no, it is exactly the same. Instead of this, if I write fx equal to sigma y modulus of x, just a factor sigma y, then I get exactly that, right. So that is it. So basically for j not equal to 0, if j is not equal to 0 all the time anyway, if j is equal to 0 or not equal to 0, we can always write the flow rule. One of the ways of writing the flow rule is that sigma 0 belongs to del phi j, correct. So what is del phi j for j not equal to 0? For j not equal to 0, this function is perfectly differentiable and it gives you sigma 0 equal to sigma y times j divided by norm of j, right, for j not equal to 0. This division makes sense, right, division by norm of j. So you clearly see that the direction, the tensorial direction of sigma 0 is the same as the tensorial direction of j. Sigma y is after all the magnitude of sigma 0. So I can write this as sigma 0 by norm of sigma 0, because that is sigma y, is equal to j, but if I just replace j by, okay, anyway, j by norm of j, but I can replace j by epsilon p dot, right. So this is epsilon p dot divided by norm of epsilon p dot, correct. So this is essentially the idea, the co-directionality, which is posited as a hypothesis in the classical plasticity, now comes as an automatic outcome, a corollary of the construction, the principle of construction of the dissipation potential, okay. So the dissipation potential, as we have already discussed, is this sigma y sigma y times norm of j. What happens now when j is equal to 0? For j not equal to 0, it is smooth, right. Of course, you also see that phi j, based on this definition, it is positive, sigma y is greater than 0 all the time, one homogeneous, and hence this particular dissipation function will be dissipation functional, will be rate independent, right. It will denote, it will conjure a plasticity which is rate independent. So it denotes, it produces a pure sphere in the deviatoric stress space based on the flow rule, correct. To get the flow rule, we need to determine the subdifferential, right. So we have already determined the subdifferential for j not equal to 0. For j equal to 0, it is again pretty simple. You can see, you remember our discussion with fx equal to modulus of x, right. So it consists of, the subdifferential will now be a set for j equal to 0, right, because there is that is the point of non-smoothness, the tip of the inverted tent, all right. So this we have already seen, right. So basically, we have already seen that for j not equal to 0, we have the subdifferential in the form of a singleton, which is sigma y j by norm of j. Case 2, j is equal to 0. Now here what happens? So you have to remember this all the time, right? 1D case, and then generalize, right, in your mind. Del phi 0 in this case, because we are at the tip of the tent. This is the tip of the tent, right? Inverted tent rather. Okay. So del phi 0 there consists of all the stresses or thermodynamic forces x such that the modulus of that or the norm of that thermodynamic force is less than equal to sigma y. Because you see, we are looking at the supporting hyperplanes, no. So here, as I have been telling you repeatedly, all these are supporting hyperplanes, correct? So basically from minus sigma y, this slope is minus sigma y, this slope is plus sigma y slope, right? And in between everything is a valid possible stress for which no plastic flow occurs until we go to the boundary, right, where there is a discontinuity in phi star and therefore there is a sudden change in the subdifferential, right. Okay, so subdifferential of phi star, I mean. Okay, so you see, so this is how basically the yield set appears naturally here. What is the yield set? Set all stresses whose norm is less than equal to sigma y, right. So also recall that this yield stress, the notion of the yield set consisting of so many stresses is how intertwined that idea is to the non-differentiability of the dissipation potential at J equals 0. That is the most important thing. Okay. So if you think, I mean, nobody can produce a perfectly differentiable smooth dissipation potential and get the yield set. It is not possible. Right, so we can actually find the Legendre-Fenchel dual of phi star. We have already seen what is it. Okay, so we already know that the Legendre-Fenchel dual for this particular case of phi is the indicator function. Within the yield set it is 0, outside it is infinity. But nothing wrong in repeating things, because these ideas are new, maybe new to you, and therefore by repetition we get to, you know, or by reinterpretation we get to understand things better. So recall again the phi star x. Let us do it again. What is phi star? Okay, so the basic definition of phi star, to start with. So in case 1, let us say that this x, the thermodynamic force, is norm of it is less than equal to sigma y, right. Now use the Cauchy-Schwarz inequality, knowing about it. So the inner product of x and j is less than equal to the norm of x times the norm of j. Now this is therefore the maximum value of sigma norm of x is sigma y. So I can actually use sigma y here, okay, because this is an inequality, right. Therefore I can say that xj minus sigma y norm of j is less than equal to 0. Right. So if you choose j equal to 0, this gives 0. So therefore phi star x equal to 0 for all norm of x less than equal to sigma y. This is what is expected anyway, right. On the other hand, if modulus of that is the norm of x is greater than sigma y, then we may take j, because everything is smooth here. So j and x are co-directional, we have already seen that. Okay, so we can actually take j equal to lambda x, right. So in that case x inner product with j minus sigma yj, so put j equal to lambda times x, you get just lambda times the inner product of the norm of x with itself, that is norm of x square minus sigma y lambda times inner product the norm of x, right. This is just algebraic manipulation, and this is what we get by factoring it out. But we have already said that norm of x is greater than sigma y, that is the case for us now. So then you see for a lambda I can choose lambda anything greater than 0, because it is still not determined, this lambda, relating this co-directionality of j and x, right. This factor lambda can be anything. So, I can choose it infinity or close to infinity, therefore, phi star goes to infinity. So, this is basically exactly the same argument that we have used earlier to show that phi star becomes an indicator function. So, we again get the same thing by repeating the argument that phi star is the indicator function as indicated here. Okay? It is the indicator function over C. The normal cone, so if C is a smooth ball for von Mises plasticity, smooth, spherical. So, the normal cone within the set C will be simply 0, the singleton set 0. Why? Because normal cone is nothing but nkx. Sorry, this should be not k, I am sorry, this is C. Okay, so we will just remove this. NC x is equal to del the subdifferential of phi star x, right. So, for x within the set C, the admissible stresses, then phi star x is 0. So, del phi star x is the standard derivative because it is a smooth function, phi star is 0 everywhere, trivial, its derivative is 0, its subdifferential is also 0, right. So, that is a singleton set. The interior point. The normal cone is a singleton set. On the boundary, what is the normal cone? You differentiate again. So, basically, so we have basically this set C, which is a perfect sphere. Think of it to be a sphere. It is not clear. Oh, I will draw it this side, okay, so that you can see. Think of it to be a sphere, okay. So, I am actually on this point. So, therefore, by associativity which we have proved, so sigma, so this is the origin of sigma 0, this is 0 stress, and then this is my sigma 0, okay, this is my sigma 0. This sigma 0 is here, right, on the yield set, on the yield surface. So, this strain rate must be directed in the same way, this is j, but I do not know the factor by which I should multiply this. So, that is so lambda sigma 0 or something, right. So, essentially therefore, nkx nk sigma 0 essentially nc sorry nc sigma 0 will be equal to lambda x. For lambda greater than or equal to 0, it is still undetermined. Lambda, the modulus of lambda is nothing but the plastic strain rate's value, magnitude, right. It aligns with the outward unique normal, all right. So, thus the plastic strain rate is again seen to be collinear with stress, just from the definition, plastic strain rate I want to find. So, that is my j, which is equal to epsilon p dot, I am repeating, which is basically in this set of the subdifferential of phi star with respect to x means sigma 0, okay. So, that is it. So, this itself says that they are collinear, they are in the same direction if it is a sphere, okay. So, there are no corners. So, therefore, there is no multi-valuedness of the plastic strain rate. The plastic strain rate is always single valued in this case, okay. So, let us summarize everything. Go through these slides again and again, till it goes into your heart. The associated flow rule is given by sigma 0 is in the set, belongs to the subdifferential of phi as a function of epsilon p dot, okay. In other words, we get the co-directionality directly from here, epsilon p dot equal to lambda times sigma 0 by norm of sigma 0, right. So, naturally this lambda has to be, because sigma 0 by norm of sigma 0 has a magnitude equal to 1, has a norm itself equal to 1. So, therefore, this lambda has to be equal to the norm of epsilon p dot. That is, the plastic flow is coaxial with the deviatoric stress. The flow direction is unique as long as the yield surface is perfectly smooth, right. The evolution is smooth, right. It is such as to create the maximum plastic dissipation. All of this we have actually seen from just one principle. that is of constructing the phi j, the dissipation potential from this support function, right. In the next lecture, we will discuss about what happens if discuss further. We have already discussed a little bit, but not enough. We will discuss more about what happens if the yield set is non-smooth, which is the case with Tresca plasticity. Okay. More importantly, because Tresca plasticity many people may not be using these days. More importantly, we will see how we can implement these ideas, the initial parts of that in a numerical code, like in the finite element. Okay. Till then, goodbye, and I will see you the next time. Thank you.